coming.
Hello, sir.
Welcome to PhilSoc. My pleasure to introduce Professor Gary Fuller from the University of Manchester to talk about star formation.
Thanks very much. Thanks for inviting me to come to talk about star formation. The title is Peering into the Dark, or Peering into the Darkness. And you might think that's, well, obvious, I'm an astronomer. But actually I'm a radio astronomer, so I can work 24 hours a day, which is an error when I start to pick which field to work on. The dark here refers to something else, and I'll explain that in a few moments. So what I do my research on is trying to understand how stars form. Okay? So I'm at the Georgia Bank Centre for Astrophysics. I'm also the lead scientist and principal investigator of the UK ALMA Regional Centre node. ALMA is a new telescope about which I'll tell you something in a moment. Here's a very pretty picture, which I hope you can see. There are several interesting things in this picture. Partly down here, this is ALMA, the new telescope. The other interesting thing in this image are the dark bits. The stars aren't very interesting. The stars are like people. Most of the population of stars in the galaxy are middle-aged, and middle-aged things are boring. So I apologise for that to start with. Young things are much more interesting. And the young things, the young stars, form in these dense clouds of gas and dust. And what you're seeing here is a silhouette. You're seeing the absorption because something opaque is in the way. The thing that's opaque in the way are these dense clouds of gas and dust, and it's in those regions the next generation of stars are forming. And those are the regions you want to observe if you want to understand how stars, like all these boring middle-aged white dots on here, form. By the way, this is a real image taken from the telescope site, the galactic plane, of course, running up this way. Okay, stars are the building blocks of the universe, and I could give you an entire lecture about stars themselves, but there's a great division among stars. There's low-mass stars and there's high-mass stars. So low-mass stars are stars with masses something like that of the mass of our Sun, and then the most common stars in the universe. An interesting bit of physics means once you get up to a mass of about 8 times the mass of our Sun, the internal structure of the star changes, and that has a profound impact on what the star does and how fast it evolves and how it ends its life. So massive stars live fast and die young. This is an example of a low-mass star-forming region. Again, you can see these dark regions which are absorbing the background light. This is a cluster of mostly young, low-mass stars forming in this cloud. This is an image of Orion, the Orion Nebula. This is a region that's forming massive young stars. And I hope you notice how energetic and bright and colourful this image is, and how it's actually quite hard to see stars in it. That's an important point. I mentioned that young, massive stars rather live fast and die young. There's a factor of 8 difference between a typical low-mass star like our Sun, with 1 solar mass, for example, and, say, a 10 solar mass star. So it's a factor of 10 difference in mass. A 10 solar mass star is 10,000 times more luminous than a 1 solar mass star. So there's a very non-linear relationship between the mass of the star and its luminosity. That has an important impact for understanding how high mass stars form and how they affect their environments. Because what you're seeing here is the consequences of star formation, not the origins of star formation. These high mass stars are also the chemical factories of the universe. I was asked for a quote to advertise a course I'm teaching at the University of Manchester, which is to non-science students. And I pondered it for a little while, and the quote I came up with is that every molecule of hemoglobin in your body has iron in it. That iron came from the death of a high mass star. So you're all bits of supernovae. We're all bits of supernovae. How do stars form? Well, you can go out and observe star formation. Or you can run computer simulations of star formation. So what you see here on the left-hand side is a numerical simulation of what happens if you take a cloud of gas and let it evolve under its own gravity, and it collapses, you get this filamentary structure, and on the right hand side this is actually an image showing the temperature of the gas, and so the spots here correspond to the locations in these models where the stars are forming. It's very hard to see in detail what's going on here. These are very complicated, very large simulations, and it's good to try and extract key stages during the evolution to help us understand what's going on. So here's the cartoon story of how you make a star. This is how you make a low mass star. High mass stars are different, and we don't quite have such a nice scenario. You start off with making a low mass star with a dark cloud, something like those black patches I showed you earlier. And you can see those. This is a real region in the sky where you can see this cloud is completely and utterly opaque at optical wavelengths. At some point, that cloud will have enough mass that it becomes gravitationally unstable. It starts to collapse, so the inward motion, gravity is drawing the material in. Somewhere deep in the centre here, eventually the density gets high enough that a star forms, thermonuclear reactions eventually start, you get a central star. This cloud, as it collapses, has some rotation associated with it. It has to. Okay? Conservation of angular momentum means that not all this material can fall onto the star. Some of it collapses and forms a disk around the star. There's an interaction between that disk and the star, coupled by the magnetic field from the star to the disk, and that drives an outflow. And indeed, some of the earliest signs you see of young stars forming is not this gravitational collapse, which is actually slow and hard to observe, but these outflows, like this. So there's a very young, low-mass star in here, and it's driving two jets of gas in opposite directions. This one's going away from us, this one's coming towards us. This gas is moving at hundreds of kilometers per second. This gas, gravitationally collapsing, is moving at maybe 1 kilometer per second. It's very hard in these kinds of regions to identify this very slow contraction that's actually feeding mass into the star, as opposed to this outflow, which is blowing material off the star. On the other hand, the outflows are really pretty. There's a young low mass star about here, and all of the colour you see in this region is resulting from the outflow from the star, blowing material away. And indeed, that outflow will eventually remove this whole clump of gas and dust, so that this star in a few million years will just be another boring, middle-aged white dot. Okay. Star formation can be very pretty, as I showed you. There was a picture of Orion. This is a picture of another bit of Orion, seen in far infrared wavelengths, near infrared, and the visible wavelengths. And again, they all look very pretty. There's lots of activity going on in these regions. That's because, as I said, these stars, particularly high mass stars, which is what's forming in this region, in here, and not in this image, but actually up here, off that image, are putting out so much energy, both in terms of radiation and wind, physical blowing of material away, that they're redesigning, resculpting their environment. The feedback from these massive stars that are forming in this region are basically rearranging the material out of which they were formed. So this clearly has an impact on the star formation. Ultimately, that impact is it destroys these clouds in which these stars form. So it stops star formation. So it's a negative feedback. But during that process, you can see it's compressed this gas here. So it's possible that the compression actually leads to forming more stars, prompting more star formation. So there's both positive and negative feedback from the stars onto their clouds and their environment. Another example, this is another massive star forming region. There's a very massive young stars somewhere in here, and they are obliterating the cloud in which they formed. This is a numerical model specifically designed to try and understand this feedback in this region. it's remarkable that you can do this kind of model and produce such a good match to the observations. But if you really want to understand the initial conditions, what gave rise to those massive stars in there that are now so important for this region and important for the chemical evolution of the universe, for producing more iron, for producing all the other heavy chemical elements. Trying to look at this kind of region is like coming along after the accident and trying to reconstruct what happened, except it's more complicated. So, what are we going to do? What do we want to, where are we going to look to try to understand the initial conditions for massive star formation? Well, you look where the light is. If all the light in this region is to do with the massive stars forming, because they dominate the luminosity, we should be looking over here, where there aren't yet massive stars. So that's what we've been doing. We've been looking in the dark regions. This background image that started this talk shows you some of the regions we've looked at. The image is actually in the near-infrared, mid-infrared, 8 microns wavelength. It's emission from dust that's being heated by the general radiation field of the galaxy. And you can see these dark regions like we saw in the picture of the galactic plane. But now, this is in the infrared, that was in the optical. These clouds are much, much more opaque. If we looked at this region in the optical, you'd barely see anything. The infrared lets us focus down to the densest, most quiescent regions, the regions that are, in the next few 100,000 years, going to collapse to form stars, and some of them, like this one, which I'll come back to, are going to form massive stars. So what we've done over the last, let's see, 6 or 7 years, is identify those kinds, or these kinds of absorption regions in a large-scale survey that's been done of the galactic plane from a satellite called Spitzer. We've identified them, taken these images and turned them into maps like this, and the contours on this map tell you where the highest column is, the highest amount of material is along the line of sight. There's one cloud. This is an example of many clouds that occur in this long filamentary structure. This is another region I'll come back to in a few minutes, where you see 1, 2, 3 of these infrared dark clouds. So we've identified about 15,000 of these objects now. We've seen them in absorption, and that teaches us something about what's going on. We can map how much material there is. But actually, it would be nice to see not the absorption, but the emission from these clouds as well. Because we can learn different kinds of things by studying the emission as opposed to the absorption. So how do you look at the emission in these clouds? Well, the first thing you need to know is that these clouds are cold. 10 Kelvin, minus 263 Celsius. What do you see that emits at that kind of temperature? The answer is dust. Everything in the universe glows. Depending on its temperature, it glows at different wavelengths. So the dust in these clouds, although we don't see it glowing at this near-infrared wavelength, does glow at much longer wavelengths, in the millimeter and submillimeter. So this is a plot that shows you wavelength on the bottom. So this is 1/10 of a millimeter here. This is 100th of a millimeter, 1000th of a millimeter. And this plot, this just shows you how bright the emission is. And the curves show you what happens if you've got material at different temperatures. Okay? This is the Planck black body function for those who've come across it already. Then the different curves are labelled by temperature. So this is the emission you get from the surface of a 10 solar mass star, for example, at 10,000 Kelvin. The emission from the surface of the sun, room temperature, 100 Kelvin, and down here would be 10 Kelvin. And for the purposes of this exercise, just note how the peak of this curve moves to longer wavelength as the temperature goes down. So at 10 Kelvin, the peak of this curve is over here at a few hundred microns. So if we want to see the dust emission, we need to look out for these long wavelengths. there are two things in these clouds. They're gas and dust. The bulk of these clouds are molecular hydrogen, and we can't observe directly molecular hydrogen at 10 Kelvin. It's just not exciting. But what there is in this gas are other simple molecules. And those molecules can be observed at these very, very low temperatures. And when I say simple molecules, I'm talking about things like carbon monoxide, hydrogen sulfide, formaldehyde, methanol, ethanol. Things you've heard of, right? Ammonia, I could put ammonia on here as well. These molecules rotate, and actually also vibrate, but primarily rotate in the interstellar medium. And we can watch these molecules make a transition from one rotational state to another rotational state. If they go from a high state to a low state, they emit a photon. That photon is at a wavelength of a few millimeters, or perhaps a fraction of a millimeter. We can observe that with millimeter, sub-millimeter telescopes. So all these species are observed in the interstellar medium. There's actually something like 200 different molecules known. You noticed I said there are simple things you knew. There are also perhaps stranger things you don't recognise. HCO+, a molecular ion, N2H+, which is also a molecular ion. This is just simple nitrogen, as makes up the bulk of the air in this room, with a proton attached to it. But in the density of interstellar space, these things are stable, and we can observe the transitions. So, by looking at the transitions of these different kinds of molecules, we can use the molecular fingerprints to measure the temperature, density, and motion of the gas. So we can look at the dust by its emission, its continual emission, and the gas looking at spectroscopy, and we can derive the physical properties of these clouds, and including how the clouds are moving. There's only one problem, and that problem is summarised here, which is, this is wavelength running from, what's that, a nanometer up here to a kilometre. It's a very long wide range of wavelengths. This shows you the opacity of the atmosphere. So at wavelengths short of 100 nanometers, the atmosphere is completely opaque. Now that's good. It keeps the ultraviolet and high energy emission from the sun off our skin, because I sunburn very easily. You'll see the atmosphere is quite transparent in the optical region. But if you go to these longer wavelengths, 1 micron, 10 microns, tenth of a millimeter, the atmosphere is opaque. When you get out to the radio, the atmosphere becomes completely transparent again. That's why Jodrell Bank manages to operate and observe the radio emission from the universe from the Cheshire Plain, where you'll notice the weather's rather poor. It's cloudy and rains a lot. You can't observe in these wavelengths of interest to me for studying this cold, dense gas and dust from Cheshire. You've got to go somewhere else. Where do you go? Well, you want to get as close to space as you possibly can. And that means going to somewhere high, somewhere flat, because you want to build a telescope that gives you the best possible view of the universe at these wavelengths. You go to this place, the Atacama Desert in northern Chile. Okay? This is a view before ALMA was built. It's a plateau. This plateau is at an altitude of 5 kilometers above sea level. This is a very difficult environment to work in. There's little oxygen, and indeed people wear oxygen masks while they're working outside at this environment. And if you're working at the observatory up here, the buildings are oxygenated, so there's enough oxygen to breathe. But you see, the sky is clear. You're above a good fraction of the atmosphere, so this is at sea level, but you can start to observe in some of these windows that open up here, where the atmosphere becomes just a bit transparent. Okay, so I mentioned ALMA, so what's ALMA? ALMA is the Atacama Large Millimeter Submillimeter Array. It's an aperture synthesis telescope optimized for observing these millimeter and submillimeter wavelengths. So wavelengths from 1 centimeter down to 0.3 millimeters, And in frequency, like that, that's 30 gigahertz to 950 gigahertz. Aperture synthesis, what does that mean? If you want to look at the fine scale detail in the sky, you need a big telescope. And by big telescope, well actually, does anyone know what the biggest telescope in the world is at the moment? The optical wavelengths? How big it is? Bigger, bigger, bigger?
19 meters.
Any numbers, anyone?
19 meters.
It's about 10 meters. There's a 30-meter telescope being built in the US, well actually in Hawaii at the moment. There's plans for a European telescope that's 39 meters. In the radio, if you want a similar telescope with a similar kind of resolution, it scales as a function of the wavelength. So instead of having a mirror tens of meters across, you need a telescope that's kilometers across. 15, 16 kilometers across. Now the trouble is, people get a bit irritated if you start building metal dishes over 16 kilometers of Cheshire, for example. Or even Chile for that matter. It's also kind of expensive and kind of an engineering problem. You get around that by building lots of little telescopes and connecting them together. You use them as what's known as an interferometer. These telescopes, these bigger ones, are 12 meters in diameter. These smaller ones are 7 meters in diameter. ALMA comprises 66 antennas in total. A mixture of predominantly 12 meter and some 7 meter dishes. As I said, to get above the atmosphere, you place it on the plateau at 5 kilometers above sea level, and this is an expensive telescope. Well, on the scale of telescopes, it's $1 billion instrument. That's too expensive for any one country, so ALMA is actually an international project between Europe, North America and East Asia. And also Chile, in the sense that the project is both based there and the Chileans donated this land to ALMA as an observatory. I should point out this land used to be Bolivia. Anyone do South American history? Bolivia is a landlocked country which has a navy. Discuss. Okay, so the thing about all those little telescopes is if you want high resolution, I said you want them 16 kilometers across. But actually, if you want lower resolution, you need them closer together. So you can pick those telescopes up and move them from a compact configuration where the separation between these telescopes is 15 meters between one and its neighbour. Or you can spread them out so that the furthest telescopes are 16 kilometers apart. Notice, by the way, each of these has these challenges. Connecting telescopes that are 16 kilometers apart and combining their signals is not easy. Having telescopes that are 12 meters in diameter and only 15 meters apart means you don't have a lot of space between the telescopes. And when they were first doing the tests for these compact configurations, people were out there watching the telescopes as they very slowly moved, because you don't want to bang 100 tons of steel into 100 tons of another 100 tons of steel. How do you move one of these telescopes from here 8 kilometers that way? To change the zoom, to change the resolution of the instrument. Well, you need a vehicle that can pick up the telescopes and move them around. So this is a vehicle, a highly specialised vehicle, into which you drive this up to an antenna, pick the antenna up, and you drive it around the desert. But first of all, you've got to get your antennas onto the desert plateau. So this shows the convoy bringing up 3 of the dishes. This is one of the dishes in place. This is one of the small 7-meter diameter dishes. This is one of the 12-meter. Here's one of the 12 meters in that carrier being moved to a new site to reconfigure the array. And by the way, I should say, if you've got these 2 telescopes, this one and its partner 10 kilometers over there, and you want to use them as an interferometer at 1 millimeter wavelength, you need to be able to measure the position of this telescope and that telescope to an accuracy much better than 1 millimeter. So you measure the position to maybe 100th of a millimeter. And that's quite a challenge. This is 100 tons of steel, carbon fibre and electronics, which you pick up, move around, put there, and you know its position to 100th of a millimetre compared to something 16 kilometres away. There's an awful lot of very, very impressive technology. But Alma grows. Here's a picture from last year. Anyone knows their southern sky? This is the large Magellanic Cloud, this is the small Magellanic Cloud. And now there are so many dishes in Alma, it actually gets hard to make decent looking pictures because they're all just white spots. The other thing you can do is you can put your telescope into orbit. So this is another telescope. This is Herschel. It's a satellite that was launched in May 2009 on an Ariane 5 spacecraft from Guyana, I believe. This is the telescope. This operates at even shorter wavelengths than Alma. So this operates at wavelengths from 0.5 millimetre to 0.07 millimetres. You have to put it in space because the atmosphere is completely opaque at these wavelengths. And this was put not into orbit around the Earth, but into orbit around the L2 Lagrange point. So in a system of two bodies, the Sun and the Earth orbiting each other, there are 5 points where you can have something in a stable orbit. This telescope was put out here at L2, which is, I'll read the numbers on there, 1 million kilometres from Earth. And this, in combination with Alma, lets you do remarkable things. So, just to show you, this is a plot that shows how much energy a young high-mass protostar emits as a function of wavelength here again. And this just shows you the bands, the 5 bands at which Herschel observed. So as I said, 0.5 millimetres to 0.07 millimetres. And it corresponds to exactly around the peak of the emission. That's not coincidence, of course. That project was designed that way. What can you do with data from Herschel? Well, this is one of our infrared dark clouds. We observed it at each of those wavelengths. And then at every position on the sky, we can make a model of the emission and ask how hot is the dust and how much dust is there along the line of sight. And what this plot shows here is the contours show you how much dust there is. So there are a number of different peaks in this cloud. The colours show you the temperature. And the interesting thing about this cloud, and in fact most of the clouds, is they're cold in the middle and hot on the outside. And notice I said 10 degrees, well this one's somewhere between 10 and 12 degrees in the centre. And this plot just shows you that in fact the temperature is coldest in the highest column density regions. What that's telling you is there are no stars forming in here. There are no stars heating the gas and dust in this cloud. But the high, what's called column density, the high amount of material in the peaks of these clouds are so high that some of them may go on to form massive stars in the future. And that was part of the goal of this project, or my interest in these infrared dark clouds, to try to identify regions that will eventually go on and form high mass stars. So, this is an image you've actually seen. It's the image I'm using in the background. Within our catalogue of 15,000 infrared dark clouds, there are several of them in this region. That one I pointed to before, and that one's particularly interesting. So here's a blow-up of it. So this is the same image. This is actually an extract from that same image you just saw. You can see the dark region, it's the absorption due to the dense gas and dust. You can see two green fuzzy things in here. Green fuzzy, by the way, is a technical term. Honestly, it is. The other technical term is EGO, extended green object. What you're actually seeing here, we're not very creative in this one. What you're seeing here is actually a composite image made of 3 different wavelengths. And the fact that you see this looks like it's green emission means that its emission is peaking in the middle of of those three wavelengths, and it's telling you that there's an outflow or some kind of activity going on in the centre of this cloud. The crosses indicate the location of what are known as masers, a very bright, intense emission from a molecule, and those you only see associated with young, massive protostars. So in the region, within this dense region, we believe there are two extremely young protostars. And you'll notice how different this region looks to the ones I've shown you before that were forming high-mass stars. The only light here is right where the stars are. These stars are not yet destroying their cloud. But this is a remarkable cloud. This region here, this is what you see when you look at it with Herschel, when you look at the dust emission. In this central region, there's 2,500 solar masses of gas. There's enough material in this tiny little region to make 2,500 stars like the Sun. If you look at the spectral line emission, the emission from the molecules in the gas, if this gas cloud were completely static, and you looked at the emission from this molecule, HCO+, you'd expect to see something a bit like this. Basically a single spectral line. You'll notice that as you go into the centre of the cloud, the shape of the line changes. And it changes to have this bright peak on the left and this little shoulder on the right. And that's quite common. Without going into the details, that is telling us about the motion of the gas in the clouds. And this kind of spectral signature